Hi Juan, this is Bruce. Thanks for contacting me. I had a great time visiting you in Colombia, and I'm really happy that you reached out to me with this question about how to choose a venous cannula. This is something that I don't think is published anywhere, and a lot of perfusionists have had to figure it out for themselves. I'm happy to help. Let's look at the graph. First of all, the graph shows us flow rate and something called pressure loss, and we'll talk about what that is. The flow clearly is what you think a top flow is for your patient. A lot of perfusionists pick a top flow of 2.4 cardiac index. Maybe for your pediatric cases you use 3.0 cardiac index, maybe even higher. I'm not sure what your hospital uses. But that's the flow that they're talking about at the bottom of the chart. So now you have a patient who needs, say for instance, 4.5 liters flow. You have to come out here and read the chart right there. Now the other question is, what is this pressure loss thing? Pressure loss is also called delta P, or perhaps pressure gradient, and it is referring to the pressure. This is your cannula. The pressure inside the cannula versus the pressure outside the cannula, P1, P2. And the difference between them is the delta P. So if, for instance, you want, and these pressure gradients are at a given flow of X, and in this case we picked 4.5. This is X down here. So if you need a flow here at 4.5, you want to know which cannula you can select, and that's going to be based on the pressure loss, the pressure gradient, that you can provide that cannula. So we need to have a positive pressure of, say, 20. If we look at 20 here, we would need to have a positive pressure of 20 to get 4.5 liters through this cannula if it crossed at that point. Let's look at this one. The 28 French would need, 30 millimeters of mercury positive pressure to drive 4.5 liters flow into that cannula. So which of all these should you select when you are picking your cannula? The delta P is based on the average height of the human being. If you've got a patient laying on a table, and that table has legs, and you have an average size surgeon standing next to that, then the distance from the patient on a table to your reservoir is going to be about 50 centimeters. So the distance from your patient to your reservoir, 50 centimeters. And if we look up the conversion rate of centimeters of water to millimeters of mercury, we see they've got a factor of 0.7. So 50 centimeters of mercury, 50 centimeters of water comes out to about 40 millimeters of mercury. So if your patient is on a table and you drain down to a reservoir by gravity, then you have about 40 millimeters of mercury driving pressure because the patient is above the reservoir. If you were to raise the bed, then this number gets bigger. If you were to lower the bed, then this number gets smaller. So we typically read these charts at around 40 because that's the kind of drainage. That's the kind of pressure gradient you get with gravity. So now let's go back to our patient who needed 4.5 liters flow. And we can see that somewhere right around here, we get a 26 French. That would be a great cannula to select for 4.5 liters flow. If we were to raise the table, then we would have more drainage, and we might have, say, 50, but there's no cannula at that position. If we lowered the table, we would only have 30. So if we had a really short surgeon, we'd have to use a 28 French, for instance. Now the next question you might have is, what about with bicaval cannulas? If we're going to drain the heart from the SVC and the IVC down into our reservoir, then we're going to take this delta P, divide by, we're going to have the same delta P, so we're going to take the cardiac index and divide by 2, because half the drainage can come from here and half the drainage can come from there. So if we remember our patient needed 4.5, let's go now, divide by 2, come back to 2.25, and we need our cannulas to cross that line right there. And if we only have gravity and the average height of the table, then we're going to have about 40. And that means we could probably do this with 2 20s, maybe even a 20 and an 18. The next thing you might ask is, what about with vacuum-assisted venous drainage? With our patient on a table and an average height above the floor, we have a drainage of 40, delta P 40. But if we put vacuum into the reservoir, we might have, instead of 0 pressure inside the reservoir like you do with gravity, we might have minus 20. Or if your institution is a little more aggressive, you might be allowed to turn up your vacuum to minus 40. I know some institutions are allowed to apply negative 60 to the head space of the reservoir for their vacuum-assisted venous drainage. Personally, I draw my limit somewhere around minus 40. So then we would have minus 40 in the reservoir, and we still have 40 difference in height from gravity. So together, the two of them now give us a delta P of about 80 millimeters of mercury, and we could read this chart as high as that with our most aggressive vacuum assist, knowing that we get 40 just by gravity. If we were to look at our patient who needed 4.5 liters flow in a single cannula, then if we're only going to use gravity, we should pick a 26. If we're going to apply a little bit more vacuum, we could use a 24. And if we apply a lot of vacuum, we could get by with a 22. And if this patient was going to be bicavally cannulated, then if we only have gravity, we need a 20 French. We need 2 20 Frenches. But if we were to apply a lot of vacuum, we could get by with an 18 and perhaps even an 18 and a 16 French, because while this is over here, this is also pretty low. So if you were applying 80, you'll get a lot more drainage. So this range here gives you the maximum capacity of your cannulas based on gravity or vacuum. So I hope that was helpful to you. Let me know if I can explain anything else. Buenas noches.